Thank you so much. It's a pleasure to be joining you today. So welcome from Cairo. I actually wished that I was able to join you physically, but maybe next time. And my today's presentation is about efficient end-to-end autonomous driving. And this is the agenda for today. I will very quickly motivate about the problem, and which is something that I believe is already there. And discuss very quickly the literature towards the existing approaches to the problem and how they are compared to each others. What are the strengths and the weaknesses of each approach, at least from my point of view. And for the rest of this presentation, I will focus on one of the approaches, which is the end-to-end approach, because from the comparisons that I'm going to discuss, I think it's a very promising approach, and I will discuss some ideas towards making it even more efficient. Namely, we will discuss what we call the CLSTM architecture, the model itself, and some trick that can be done on the classification layer to further improve autonomous driving performance. And after this, I will discuss how we can further improve end-to-end autonomous driving by improving the conditional imitation learning model, and how we can rely on classical techniques like occupancy grid map for further improving the performance in terms of doing steering rectification based on that OGM. That OGM or occupancy grid map is known for being very heavy computationally, and it has some demanding memory footprint. So how can we make it more efficient? And after this, I will discuss some experimental results regarding the ideas that I'm going to present and conclude my work. Quick motivation about the problem. We have 1.3 million people are killed on road accidents, unfortunately, every single year. To put this into perspective, it's equivalent to having 7 Boeing airplanes falling out of sky each single day. This mortality rate is higher than deadly diseases like HIV, and this is besides the huge property damage and the people who sustain non-fatal injuries. And 90% of traffic crashes are due to human mistakes. And the vision for autonomous driving is to be crashless. This is not because they are smarter than humans, but because computer is paying attention to the road almost all the time. It's not only about safety, but in terms of mobility. As you can see, it will provide greater access to elder and disabled person, and it can increase the traffic on the road without adding any extra infrastructure. Studies say also that due to technologies like car platooning and things like this, energy consumption savings can be as much as 90%. And plus those cars will have like new social effects and aspects like reducing car ownership and things like this. Usually cars are sold to us like this, but this is actually how real driving looks like. It is not sunny, it is usually rainy, and you might prefer to do anything in life other than to drive. And the reason why this is that traffic is really getting worse. In the United States, from 1990 to 2000, vehicle miles increased by 80%, while they rose their roads infrastructure by only 37%. If you multiply the average commute time for a person in the United States by the number of workers in the United States and divide this number by the average lifetime expectancy of a human, you will find that daily in the United States alone, people waste 90 complete lifetime in commuting just to go from place A to place B. And this is a huge waste of time. You might prefer to continue your work during that time, or maybe carry on a conversation with passenger. So this is a huge waste of time. Despite all of these benefits, still autonomous driving is believed to be still decades away. I quote this sentence from a literature paper that's well known in the domain, which says that autonomous driving in fully autonomous navigation in arbitrary complex environment is still decades away. That was in 2017. And in a more recent autonomous driving challenge related to Carla simulator, one of the key conclusions actually was that driving is far from solved, even in the presence of privileged information that's provided by the simulator. And the journey of autonomous driving is not very recent, actually. It started from centuries ago, from the concept of magic carpets, which combined the two once fictitious dreams, flight and autonomous driving. While flight is not a far-fetched dream anymore, still autonomous driving is not fully achieved. Promising trials in the 50s have been conducted by automating very small section of public highway in the United States by installing sensors on the pavement that detect metallic vehicles and send guiding signals to guide the vehicle. It did very well on the level of action, but it did not do any perception at all. So it is not a very, it's not what we want from developing autonomous driving. The first autonomous driving that does perception and action was in the 80s of the previous century. This Alvin car from Carnegie Mellon University, but it was driving in very specific conditions. And with the DARPA Grand Challenge in 2010, which captured the attention of the press and the inspiration of researchers, we started to have lots of autonomous driving programs in lots of companies, even from outside the automotive, like Google, which started its autonomous driving program in 2010. Nowadays, we can see level 3 autonomous driving vehicles for conditional automation, but still level 4 and level 5 are not yet achieved due to the problem being more challenging than we have expected. Actually, in this paper entitled Autonomous Driving in the Face of Unconventional Odds that I published recently with Dr. Ibrahim Sobh, which is actually Dr. Ibrahim will be the next presenter. He will deliver the presentation after my presentation. We published this paper in the Communication of SEM journal, where we discuss the unconventional odds that are facing autonomous driving, with focus actually on developing countries. Challenges are not only technical. You have legalization challenges, cultural challenges, consumer acceptance, actually lots of challenges. So the problem is not solved, and we can see news regarding crashes that are happening from trial self-driving vehicles. So what is the situation at the moment? I can actually split the existing approaches to autonomous driving into 3 categories. First, the mediated perception approach. Second, the end-to-end approach. And third, the direct perception approach. For the mediated perception approach, the problem of autonomous driving, despite it's a complex problem, it can be looked at as a problem of predicting just 3 numbers: the steering wheel angle, the pressure on the throttle pedal, and the pressure on the braking pedal. And the mediated perception approach tries to split this big system into subsystems. Each system does specific job, like object detection from camera, like semantic segmentation from LiDAR, like road lanes detection, like static free space detection, and eventually combine all of these information to predict the 3 numbers. The split of such subsystems does not guarantee to maximize the overall performance of autonomous driving, because actually the criteria of splitting this problem into subsystems is to make it easier for us as humans to understand the function of every subsystem, and this does not guarantee that it will maximize the overall objective for predicting these 3 numbers actually. And you might be doing lots of efforts that might be irrelevant to the autonomous driving task. So you are adding unnecessarily complexity to an already complex problem of autonomous driving. And also many of these subsystems require extensive data annotation. The end-to-end approach actually tries to mitigate some of the drawbacks of this approach by learning the problem end-to-end using deep neural network. And usually this is happening as having 3 regression problems, predicting 3 continuous values for the 3 values to be predicted. Actually, the model that appeared in the 80s was based on autonomous driving that was improved by the NVIDIA work in 2016, and improvements started to happen since that time. Because one main drawback of the end-to-end approach is that it cannot see the bigger picture of the situation, and it can hardly learn to do strategic planning. For example, the end-to-end approach is watching the data of a human expert driver during training time. So during intersection, if that human driver decided to go left, you are telling the neural network that going right, going forward, which are safe decisions to make, are not as good as taking left, because the human driver decided to go left. And this is the only ground truth that the end-to-end approach is seeing. And this is actually confusing the machine learning algorithm. The direct perception approach tries to cope with this by predicting or learning to predict end-to-end some key affordance indicators, like what is the distance from my car to the car in the front, what is the distance to the left lane, what is the distance to the right lane. And it learns those indicators end-to-end, and eventually rely on a rule-based controller to combine all of these predictions to provide the driving 3 commands. But unfortunately, the rule-based controller might be as expensive as the rule-based controller of the mediated perception approach, and there are lots of heuristics involved, and even the choice of the key affordance indicator does not guarantee to be optimal. So as you can see in this table, I try to summarize the advantages and disadvantages of every approach, and we almost discussed all of them while I was talking. And as you can see from this table, green means advantage, red means disadvantage. As you can see, it seems that the end-to-end approach is very promising because it is associated with few disadvantages. And the more recently, actually, one of the main disadvantages of the end-to-end approach regarding not being able to see the bigger picture of the situation and the machine learning algorithm confusion problems that we discussed were solved by the conditional imitation learning approach that was proposed by Intel, which made the end-to-end approach even more promising, actually. And in this model, actually, instead of having a single output of the deep neural network, we can have separate branches where each branch is specialized or trained on some driving policy during intersection. So one branch is trained only on going left during intersection. Another branch is trained only on going right. Another branch is trained on following lane. Another branch is trained on going straight during intersection. And you should have a route planner on top of this that is based on the destination to reach, should decide from which branch should I take the output to guide the vehicle to reach the destination eventually. So it's very promising, and the results were very encouraging. Actually, the results of this conditional imitation learning approach are the reported ones in these blue columns you can see. It's very promising compared to other approaches, but if you can look closely to these numbers that were reported in 2018, you will find that we have a generalization problem to new environments, because here performance is very well. This is the success rate on the Carla autonomous driving benchmark. Success rate is very well, but performance dramatically decreases when the car is tested on a new environment that was never seen during training time. And if you only change the weather condition, you will find that the driving policy is not very systematic. So it is inconsistent against varying weather. This is the second drawback. The third drawback is that the vehicle cannot avoid unexpected route blockages, because if you rely on a route planner, which is like Google Maps. Usually route planners like this cannot detect that this route is blocked due to a working zone. So if a route is blocked as a for a working zone, which are ever increasing in numbers, by the way, it might tell the vehicle to go right, and the model branch that's associated with going right will crash with this work zone. I will discuss how we can cope with the first two problems, but regarding the third problem, maybe in a coming event, I will be able to discuss this, because at the moment we have contributions in this regard, but it remains confidential at this moment. So as I said, the majority of end-to-end approaches tackle the problem as a regression problem. Usually that end-to-end approach relies on a convolutional neural network, which is computationally expensive. So they try to avoid learning temporal dependencies through LSTM and things like this. There is actually room for improvement there, actually. We can learn temporal dependencies because it's very important for learning a good driving policy, because we as humans do not take driving decisions based on what we see right now, but based on maybe the last like 5 to 6 seconds, and we can expect computers need to learn this information. The second thing is that the problem, the problem by default is a regression problem. That's okay. But in other application domains, like this paper here, which the authors try to detect the apparent age from images, which is also a regression problem. But when they transfer this problem or pose it as a classification problem, that end-to-end neural network performs even better, just by transforming the regression problem into classification problem. And you have one output neuron associated with every age, or maybe in our problem, every steering wheel angle or pressure level on the throttle or the braking pedal. Because neural network actually is very efficient in discrimination tasks. So we can transform our problem inspired by other application domains to classification, and we can even improve the performance. Also, the majority of end-to-end approaches rely on the camera sensor, but if we can encode the LiDAR information and do some sensor fusion, we can cope with the inconsistency again in varying weathers problem and the lack of generalization problem associated with the conditional imitation learning approach, because actually LiDAR is less sensitive to ambient light, and it has some good characteristics and drawback, of course, compared to the camera, and fusing both sensor information seems the better approach to deal with. And also borrowing from classical techniques like occupancy grid map, some advantages that can make us rectify the final output predicted end-to-end from the neural network can even further improve the problem. So we can, as we can see in this model that we proposed a few years ago, we propose a model that can learn the temporal dependencies of driving by adding an LSTM layer after the CNN. And all of this pipeline we can reduce the computational complexity of all of this pipeline by relying on techniques like knowledge distillation, model pruning, model quantization, and techniques like this. And currently, actually, we are investigating the vision transformers to reduce the computational complexity further and still being able to learn those temporal dependencies. And inspired from that paper we discussed, we try to pose the problem as a classification problem. But actually, we noticed that there are two drawbacks if you transform the problem into classification, that if you cope with these drawbacks, you can even maximize the gain from transforming the problem into classification. So when you have a classification problem, you do not by default have any spatial relationship between the output layer neurons. Because usually you have a class for human, you have another class for maybe building, road. Usually in a classification problem, you don't have a spatial relationship between the output layer neurons. But because this problem was originally a regression problem, if you during training impose that spatial relationship between the output layer neurons, you can further improve the performance. And also you can even increase the number of outputs of the neurons safely, because normally if you increase the number of neurons at the output layer, you need more representative samples. So you need to be careful with this problem. So we can impose the spatial relationship between the output layer neurons by avoiding the cross entropy, negative log likelihood loss function, and relying on new ideas like this idea. By the way, if this is the prediction of the neural network, and this is a ground truth neuron, and you have a very high activation here, this is case 1. And if in case 2 you have an output like this, where you have a very high activation just near the ground truth neuron, the old loss functions will treat those 2 examples equally bad, while the second example is much better indeed. So our method is to try to learn some sinusoidal functions that encode the value to be regressed, and learning it that way is imposing spatial relationship between the output layer neurons and cope with the 2 drawbacks that are mentioned. The equations and all of the details really associated with this method are available in paper publications we published. For this, you need to add a decoder and an encoder during the training and testing time respectively. And during testing time, you need to fit the output to the nearest sine wave via least squares regression in order to decode later the value of interest that encodes the steering wheel angle, which is in this example was the phase shift of that sine wave action. Currently, actually, we investigate other methods that impose that spatial relationship, which is namely adding the co-occurrence matrix phase loss to the cross entropy loss, which is actually showing very initial promising results that we are going to publish very soon. And very quickly, you can add the LiDAR input at the feature level to the camera input to the conditional learning imitation approach by encoding it as a polar grid view representation, as you can see from this image. And it becomes very important to rely on data augmentation pipelines, applying photometric and geometric data augmentation. And it's very important to inject temporally correlated noise during training time, because if you train the autonomous car on ideal driving, it will never see bad situation where the vehicle was about to hit the road pavement and the driver is recovering from this situation. So in testing time, if situation like this were faced, the vehicle will not learn how to recover from this. So it's very important to inject things like this during training time. In this part of the file, the patent here, we propose a resource efficient occupancy grade map that is faster and more accurate than the famous one that's used in literature. And our model actually makes use of unreflected LiDAR beams because they still indicate very useful free space information. And it tries to position the vehicle on the local grid map more efficiently in a way that make us avoid doing any map sub-pixel shifting operations to do ego motion compensation or any vehicle rotation. And also it allows us to utilize the limited area of the map to the information that's useful to the current driving situation. Because, for example, if the vehicle is going in a very high speed, you will find that most of the map area is utilized for what's happening in the front of the vehicle, not backside the vehicle. So it provides better memory utilization and faster map transformation speed. And these are some examples from data that are recorded in Bietigheim, Germany, in Stuttgart. And this is showing our occupancy grid map in action. And for this also we remove some dynamic objects that are detected from the camera stream, as you can see from this video on the left. For the occupancy grid, for the conditional imitation learning approach, you need to rely on efficient route planning algorithm. Also, we have this algorithm, which is published recently in a paper. And this is how the occupancy grid map can rectify the steering wheel angle, because if you have a very simple motion model predicting the vehicle trajectory in the future, you can query the OGM for occupancy along this trajectory, and if you have maybe some obstacle or something like this, you can slightly rectify the steering wheel angle detected by the end-to-end approach. Let's very quickly discuss some motivating results out of these methods that I'm discussing. So the CLSM model is tested on the AI dataset, and we test the accuracy by the root mean square error between the predicted value of the driving commands and the ground rules. And we introduced actually the whiteness metric, which measures how much stable are the predictions. And as you can see from those results, classification by sine wave fitting is improving the root mean square error compared to regression. And learning the temporal dependencies actually provides much better whiteness. It provides 87% of stability improvement. Again, this is happening on the computational complexity, but we are improving on the computational complexity. These are samples from the occupancy grid map that we produce in action. Also, the analysis regarding the different choices of the algorithm are mentioned in one of our recent publications. And regarding improving the conditional imitation learning approach, we benchmark on the Carla autonomous driving benchmark, which happens on lots of weather conditions and different towns. And as you can see from what we say, fusing the camera and LiDAR copes with the lack of generalization issue and improve weather consistency from 1.3% to 5%. And driving success rate improves by around 4 times from the details in this result. And further rectifying the steering wheel angle based on the OGM further improves the performance, as detailed in these tables that can be seen in our publication. And relying on a more efficient route planner compared to the route planners that was used on the original conditional imitation learning work, further can improve the performance. And this is not only on the success rate of the different experiments, because the Carla Autonomous Driving Challenge benchmark is having several tasks, several weather conditions, and it measures the success rate on these tasks, but also it provides infractions analysis. So by comparing our techniques, improvement in terms of infractions analysis compared to the state of the art, you can see that our methods are improving the infractions in the majority of types, but still not all of them, which is telling that learning the problem as a classification while imposing spatial relationship between the output layer neurons is helpful. End-to-end approach is very promising overall. Fusing LiDAR with the regular camera stream input seems very promising in coping with the lack of generalization and inconsistency, again, varying weather's problem. Classical methods like occupancy grid map can still be helpful with recent methods. And overall, those methods are a clear indicator that there are very promising results towards autonomous driving, but still, fully autonomous driving in complex environments is still not very well achieved if we want to produce reliable and safe autonomous driving. And other aspects of the problem actually needs to be investigated, like detecting the roadway readiness for autonomous driving, like what we do in this work that's published recently how to estimate the roadway readiness for enabling or disabling ADAS functions or autonomous driving. And in this work, actually, we detect roadway objects based on a data that we collected from Greater Cairo, covering 473 kilometers of route of different types, highway, midtown, all of the types. And the data is publicly available. If anyone want to use it, please feel free to ask for it. And in this data, actually, we detect the different roadway safety, and the system tries to automatically create like topological maps indicating where are the different kind of problems on roads to estimate their readiness for autonomous driving. And of course, detecting slanted objects from camera perspective requires that you treat it carefully with your model. So we introduce a new object detection method that can detect slanted objects more efficiently in this paper. Last but not least, it is very important to monitor driver.
Good time for time. So could we just bring this to a close? This is fascinating. But if you could wrap up, that would be very helpful.
Thanks a lot. It's very important to also monitor the driver and tell whether he is his situation is applicable for allowing for level 3 autonomous driving or not. Or for this, we provide this work and we provide our publicly available data set used by all of these institutes. And thank you so much.
Thank you.